the last day of the workshop. So I think by now people know the drill, but just as a reminder, we'll have 2 talks this morning. There will be the talk and then some portion at the end for questions. And then after both talks, there will be time for informal discussion with both speakers. So if you have any question that you're afraid to ask when the talk is being recorded, you can save it for the discussion. If you have questions during the actual talk, you can either type into the chat or you can just unmute yourself and ask your question during the talk. Please keep your speaker muted unless you have a question that you're asking throughout the talk. All right, so without further ado, it's a pleasure to have Pawel Caputa tell us about complexity of energy momentum circuits in AdS CFT.
Okay, thank you very much. And I would like to thank the organizers for giving me the opportunity to speak during this wonderful workshop. Okay, now, so the outline of my talk will be as follows. I'll first give a brief motivation and introduction of some basic concepts that I will use later in my talk. I'll try to be pedagogical so both communities can understand these basic concepts that I'm using. Then I'll talk about 2 approaches towards complexity in holographic CFTs, one based on the Liouville action in 2 dimensions and the other one on energy momentum circuits. And then I'll talk about recent developments, and finally I'll conclude and post some open questions. So this talk will be based on a bunch of papers, and after I agreed to give a talk during this wonderful workshop, the organizers sent me a list of papers that I should talk about. So I got a bit surprised, but actually, fortunately, some of them were mine. So this was actually a very nice homework for me. So I got to read a lot of recent developments that are, of course, related to either path integral complexity and energy momentum circuits that I didn't have time to read carefully before. So I would like to thank the organizers again for giving me this interesting homework. But let me warn you that let me ask you if some of the authors of these papers are in the audience. When I'm saying something not exactly precise or in the lack of time, I will not have maybe enough time to clarify some statements. Please step in and then correct me. I'll be grateful. Okay. So one of the reasons that we are in AdS CFT, we're interested in thinking about complexity problem comes from the very interesting computation due to Hartmann and Maldacena that studied time-evolved thermophile double state, as you already heard in several talks. And one of their findings after the computation was that entanglement entropy computed on both sides of the thermophile double state between some intervals A and B saturates pretty quickly after time of order the size of the interval. But the geometry that is dual to this thermophile double state that evolves with time still grows with time, namely the Einstein-Rosen bridge that connects 2 of the asymptotic regions still linearly grows with time for at least exponentially large times when we contrast classical gravity. So this motivated Lenny to state that maybe entanglement is not enough in our program of determining geometry from entanglement in AdS CFT, and we need something more. And he asked more precisely, what is the CFT dual of this Einstein-Rosen bridge growth in this thermophile double state that evolves with time? And the answer he gave was that it must somehow be related to the circuit complexity of the thermophile double state. And with a series of very interesting works with his collaborators, they proposed 2 interesting and well-defined objects on the gravity side, namely the volume of the extremal slice and the Wheeler-DeWitt action that should be related to this complexity, at least on the holographic side. But the expectation, maybe general from these works, is that somehow the complexity should know more than entanglement and should be related to more fine-grained information about dynamics of GR that knows about the growth beyond the saturation of entanglement entropy. So at least my personal motivation from this problem and from this development can be summarized in 3 questions. One is very kind of maybe simple and down to earth, namely, how do we see this growth of Einstein-Rosen bridge with maybe more standard quantum information tools before going to AdS CFT? Or namely, this calls for a very kind of nice and precise definition of holographic distance that would help us to distinguish between states and should be computed on the gravity side and in the CFT for a longer time. And this actually should be developed better, because I think at present we don't really have such a distance that could be used to in this computation of time-evolved Einstein-Rosen or time-evolved thermofield double state. The second question is as follows: given these two interesting proposals, volume and action, we might ask, what is the CFT dual of these gravity quantities? This helps us. This might help us. Answering this question might help us to develop further our understanding of quantum information and quantum computation tools in AdS CFT, because up to now this has been like a really kind of guesswork that has very nice, interesting checks in various precise setups, but we don't have a kind of precise machinery that will tell us which or precise sets of conditions that will tell us which tools from quantum information or quantum computation are exactly holographic and which not. And these two additions are very interesting setups to study it. And finally, this is for complexity enthusiasts. Given the very interesting story and history of entanglement and quantum information in AdS CFT, it is very likely that complexity will also teach us something very interesting about the duality. So we might as well just study complexity on its own in quantum field theories and holographic CFTs. So these are my three main motivations. Okay, are there any questions about this part? Okay, great. Then I'll go to the basic introduction. And in the rest of my talk, I'll be talking about conformal field theory. So I'll quickly review some basic minimum of basic ingredients. This could be, of course, the whole course, but I'll try to be brief. So when we talk about conformal field theories, we have in mind some theories that are invariant under changes of the background that locally preserve angles on the metric on which we are studying conformal field theories. So this can be summarized as some transformations of the metric that result in basically a scale factor omega square in this first part. And this is in arbitrary d dimensions. But in 2 dimensions, this is very special because we only have, let's say, 2 complex coordinates, z and z bar. And the set of conformal transformations for the symmetric group is infinite dimensional, and we can consider some arbitrary diffeomorphism, some functions of z and z bar, and they change the metric in this particular way. So omega square is just the product of these 2 derivatives of the functions f. And the very special object in conformal field theories is the energy momentum tensor that can be defined as the response of your theory or your action on infinitesimal changes of the metric. So if we change the background metric of your conformal field theory on which we are studying the theory infinitesimally, then the action changes proportionally to the stress energy momentum tensor. And in most of the kind of well-behaved theory, this energy momentum tensor is symmetric, conserved, and this conformal symmetry implies that, at least classically, the trace of the energy momentum tensor is 0. So in 2 dimensions, this implies that we only have 2 components, 2 independent components of the stress tensor. This will be T of Z, and this is ZZ component in complex coordinate, and Z bar complex in complex coordinates. These are 2 independent stress tensors that I will use later. And they are chiral and anti-chiral respectively. So they only depend on each one, either on Z or on Z bar. And the other thing I'll need about conformal field theories, now I'll specify into 1 + 1 dimensions, is that this group of these diffeomorphisms are unitarily represented on fields of the conformal field theory. And the stress tensor by this unitary is F, and the stress tensors under the action of this unitaries transforms in the usual way. So it's multiplied by the derivative of the diffeomorphism times the Schwarzian derivative. So this curly bracket denotes the Schwarzian derivative, and it's proportional to the very important number in CFT, namely the central charge that measures the effective number of degrees of freedom. in the conformal field theories, we can also define families of, we can also define primary operators or quasi-primary operators labeled by some dimensions, conformal dimensions h and h bar. And if we apply these unitaries on the primaries, the transformation is as follows. They're just multiplied by the derivative. And similarly, if we use the anti-chiral transformation, we would have just the derivative of anti-chiral times h bar. And the stress tensor itself plays a very important role in the CFT. Also, that it actually is very closely related to this group of diffeomorphisms, namely that if we take the infinitesimal diffeomorphisms like this f equals to z plus some infinitesimal function, the stress tensor itself is a generator of this infinitesimal conformal transformations. So the charge associated with this transformation is expressed in terms of the stress tensor, independent stress tensor components T, and also T bar for respectively F bar. I'm sorry, most of the time I'll be writing only chiral components, but I always have in mind that I have some two functions, two independent functions, and this epsilons and correspond to this F, and epsilon bars correspond to F bar. Okay, so these stress tensors, T and T bar, they can be expressed in the basis. This is just a Laurent expansion on the complex plane, and they can be expressed in terms of basis generators that form an algebra. And in two-dimensional conformal field theory, this is actually in the quantum conformal field theory, this is the so-called Virasor algebra that is a central extension of the algebra of diffeomorphism. So there's an unusual term here that has a central charge, and this is for the central extension. This is, of course, very simplistic, so I apologize for being so brief, but for the purposes of my talk, this will be more or less enough. And let me also state that in the AdS CFT correspondence, the T mu nu, the energy momentum tensor, is actually dual of the graviton or the metric. So this will also be interesting and play some role in the back. Yeah, I have one more slide about the full setup. I'll actually not need that because in most of the talk, I'll only talk about the symmetry of the CFT, so the two copies of the Virasoro, but maybe you should know that that the full setup of the CFT consists of these two energy momentum tensors and the set of primary fields, including the identity operator that has dimensions chiral and anti-chiral 0. And we consider so-called descendants operators that are obtained by taking the primary fields and its derivatives, as well as normal ordered product with the stress tensors. So actually, the full setup that we might be interested, that we are interested in when we talk about complexity in CFTs is two copies of the diffeomorphisms times R, which is the Virasoro algebra, as well as commutation relation between these LNs and the modes of the fields that can be expanded also. And also the commutators between the modes themselves that can be expressed formally in this way. And they only have two non-trivial ingredients, namely these coefficients Cij and Dij. The Cij's basically are 3-point function coefficients and Dij's are 2-point function coefficients. And once you specify those two numbers, the set of those two numbers together with the spectrum, then this is more or less all you want to know about your conformal field theory. So this is the setup. Okay, are there any questions about this part? I know it was a bit brief and fast, but please bear with me. Maybe if you got lost, I'll repeat some parts a bit later, at least for quantum computation next. Okay, so the part from quantum computation that we will need, or maybe more like from geometric approach to complexity that we will need, will be basically this Nielsen approach to complexity that was already nicely reviewed by Rob. And this came about very early in the story of holographic complexity, probably in the original works of Brown and Susskind, but also works on the complexity of coupled harmonic oscillators and free fields by Rob and also Michał in their earlier works. So in this geometric approach to complexity, we are thinking about some quantum circuit that takes us from some reference state to a target state. And this quantum circuit is defined by a unitary, that is a path order exponential of some local Hamiltonian HT, or local in time Hamiltonian HT. And then we can expand this HT in terms of some algebra of generators. So these are these MIs, so as maybe you remember from our talks. And on this geometry, the set of these unitaries define a geometry. And on this geometry, so this is some space of unitaries. And on this space, we can define some natural metric. I'll talk more about that, but this is of course non-unique. But this metric gives us a notion of geometry in a sense that we will be interested in this geometric approach to complexity. We're interested in computing geodesics in this Nielsen geometry. So in other words, computing complexity or complexity of implementing certain unitary is associated with the geodesic distance, maybe length or the energy, between, say, identity or some reference operator and the particular unitary up to some tolerance. So the nice thing about this Nielsen approach is that somehow we can think about the optimal circuits as a free fall between, say, identity and some particular unitary. But in a way, it reduces to in questions about complexity to classical mechanics or motion of a particle on a group manifold for a certain maybe complicated groups. This maybe might sound for you actually similar to AdS CFT in a sense that we are talking about something classical, but actually we have in mind something very quantum. And in AdS, also there's this quantum classical correspondence. Okay. But the last thing about this complexity is that maybe let me just give you some very simplistic version of or explanation why exactly in holography we chose this proposal, or why do we think that this Nielsen complexity is appealing. This is mostly because it kind of gives us a geometric notion of complexity, namely the distance. And given the metric G mu, we can compute this distance, or we can study geodesics on any manifold by studying the length and the energy. So the equations of motion from the length are a bit complicated, but that's why we usually study the equations of motion from the energy, and this is the standard geodesic equation. But of course, they are equivalent. And the problem itself of studying the geodesics, solving the geodesics equation may be simpler or more complicated depending on our choice of the metric. But somehow that's not the whole point of the complexity program. We can find the solutions, but of the geodesics equation. But the main problem, what makes this problem slightly more difficult than studying usual problems in GR, is that now we have fixed boundary conditions, namely some initial boundary condition and final boundary condition up to some tolerance, and then we have to find the shortest geodesic that goes between those two. So even though sometimes it might be easy to find the solutions of equations of motion, finding the solutions that goes between those two in the shortest possible way might be a bit more difficult. Okay, and my final comment is that, well, especially also don't get tricked, because this whole program, in the whole program of geometric approach to complexity, we have basically, we reduce complexity to classical mechanics, and this is something we very well know from early studies of undergraduates in theoretical physics. But of course, we want to apply this problem to holographic CFTs or QFTs. And then we have to know more precisely how do we associate points on this Nielsen geometry with data of the QFT. Are we thinking about transformations or more like states? And how do we think about these unitaries and holographic geometries? This is quite non-trivial. And finally, maybe for complexity experts, it may be a bit surprising. Why do we exactly care about the complexity being a number? So in AdS CFT, we actually need, if we want to have a good tool in AdS CFT, at least for our understanding of AdS CFT up to now, is that we need this to be a number, in a sense that in AdS CFT, we have some conjecture on how a particular quantity is computed on both sides of the correspondence, and we compute it in AdS and in CFT. And if our identification is correct, this number should match. So for energy and for the length, both numbers should agree if we use the proper length parametrization, for example. And okay, so this is of course the this is all I will need from the basic data. Are there any questions about what I have said so far? Okay, great. So before I proceed with the story of complexity in to the CFTs, let me remind you a little bit, let me remind you the story of entanglement into the CFT that kind of shares some features with the program that we are trying to follow now. So entanglement entropy in two-dimensional conformal field theories, at least for the vacuum in the single subregion A, is very universal. Is proportional to the central charge, the object I showed you before in CFT, and basically it just depends on the length of the region A in this way, and the non-trivial part of this entropy on this formula is also the cutoff epsilon. This will also be important later. The C1 is some non-universal constant that might vary from CFT to CFT, but in holographic CFTs, we are interested in the C being large. So this will be the leading contribution. And this formula has been known for a long time, so you see that already from 90s, but it got its second life after the works of Calabrese and Cardy that computed it again using so-called replica trick. And in the replica trick, we compute entanglement entropy, or this von Neumann entropy of the reduced density matrix, as a limit in a family of Renyi entropies analytically continued in this replica number n. And what Cardy and Calabrese noticed is that when we compute this trace of the reduced density matrix to the power n, we can actually express it as a ratio of partition functions on some curved background. And this curved background is some replicated background with cuts that has non-trivial curvature. And you can use these facts and compute this ratio as being by basically something proportional to the two-point function of certain operators in conformal field theories. So in two-dimensional CFTs, two-point functions, actually in CFTs, two-point functions are completely universal and fixed by conformal symmetry. So that made this result very universal and applicable to many other setups. But the main message about this replica trick that I will use later is that you can think about it as basically taking the Euclidean partition function, coupling it into the geometry and looking at the response. And the response in this case for this particular geometry with cuts is the two-point function. So in the sense that replica, so this is kind of replica algorithm, I would say, maybe in the more general terms, or more geometric terms. And maybe two comments are that this replica trick, this trick of Cardy and Calabrese made sort of quantum information computable. So in a sense, we have some very kind of abstract quantity from quantum information that we can compute in conformal field theories in a universal way. So two-point functions, they also transform under conformal transformations. And we can use that to compute entanglement entropy at finite size and temperature. We can also, this is the Euclidean computation, but we can continue it analytically to Lorentzian time and use it in the computation of quenches. And in particular, the result of Hartmann and Maldacena that I mentioned at the very beginning is the computation based on the replica trick and the correlation function of twist fields at large central charge, analytically continued in the Lorentzian time t. The drawback of this replica trick is that the price to pay for this computability is that in some sense we are losing the information from quantum information, in a sense that this two-point, we don't really understand from the perspective of CFTs, or at least to my knowledge, how to interpret two-point function in terms of quantum information, or in other words, like what's the operational meaning, where are the LOCCs or EPR pairs or everything we know about entanglement entropy hidden in the two-point function. That's somehow the price to pay for the computability. Okay, so this is just a comment to have in mind before I start with complexity. Are there any questions about this? Okay, so the first part of the story that I would like to talk about is the work I did in Kyoto with Nilai Kundu, Masamichi Miyaji, Tadashi Takanagi, and Kento Watanabe. And the question we asked in this whole discussion about complexity was, how can we compute complexity of Feynman path integrals in general? Or namely, the basic tool, when we talk about states or wave functions in quantum field theories or in quantum mechanics, the basic tool to compute or define them is the Euclidean path integral of Feynman. And the wave function is defined as the Feynman path integral. It's a functional of a boundary condition, this phi, curly phi 0 of x. And we do it as a formal path integral over all configurations of fields phi with the Euclidean action, this is Euclidean action of your theory that is a function of these fields, with a fixed boundary condition on the Euclidean plane. So this is Euclidean time, let's say at t equals 0, where we fix this boundary condition phi 0. So this is a very formal expression, and very often we don't really know how to compute it precisely, but this is a definition of a wave function or of a state in arbitrary quantum field theory. So the question we wanted to ask is how to quantify its complexity. This was our problem. And basically, the way we did it, or the proposal, was very strongly motivated by tensor network. And we did it in the, we came up with this idea of path integral optimization that you can think pretty much as a replica trick for complexity. Namely, we propose that in order to compute the complexity of a path integral, you have to go through some procedure of so-called path integral optimization that basically is based on introducing a background metric or coupling the wave function, the Feynman, coupling the wave function, the computation of the wave function to a non-trivial background. This is a resemblance of the replica trick. And so more precisely, the original path integral in the quantum field theory is computed on the Euclidean plane that we put here with some mesh, mesh of a flat space here. And here at this tau equals to epsilon, we impose a boundary condition for all the fields of the theory. And then this is, of course, a very complicated object to do, to evaluate explicitly, but we propose that in order to do it more carefully, we can actually introduce a mesh on this background itself, and as far as we go in the direction of tau of the Euclidean time, then we can actually do a less and less, or kind of perform a more or less coarse-grained computation of the path integral, and this is governed in the continuum limit by introducing the metric G on the background. Then there is some kind of optimization procedure that will not be relevant for the computation, but basically in this optimization procedure, we are getting some kind of optimal geometry that resembles a hyperbolic space, as similar to the discussions of tensor networks and AdS CFT. But coming back to the complexity story, the way we define this path integral complexity is by taking the ratio of the wave function computed in the non-trivial background, the ratio to the function computed in the flat background. And we claim that this is generically given by exponent of some functional of the metric that we then optimize with the fixed boundary conditions on possible choices of G. And after we optimize this functional, we define the path integral complexity as the minimal value of this I psi of G for a particular state. This was our proposal and the definition.
Question?
Yes, please.
I'm not clear about this optimization procedure. What is this? Can you explain that a little bit more?
Yeah, I'm going to, maybe in the next slide, in the context of 2D CFTs, it will be easier to explain, so I'm going there. If it's still not clear, please ask me again. So this was, in the first slide, it was, this slide was very abstract, but if we go into the setup of two-dimensional conformal field theories, we can basically, by the uniformization theorem, all the metrics that we can choose in 2D can be written as the flat metric multiplied by some Weil factor e to the 2 phi of tau and x. And actually the ratio, the ratio of these wave functions is very universal. So it was computed. It was shown by Polyakov a long time ago that if you basically compute this ratio of the wave function, or you'll get the exponent of the Liouville, the famous Liouville action, by this procedure. Or this is more precisely, this is related to the fact that the measure of the path integral transforms is related in the flat space is related to the one in the curved space by exponent of the Liouville action. And this Liouville action is very universal in the way that this is proportional to the only one information about the CFT, namely the center charge. It contains two pieces. The first one is the kinetic term, which is quadratic in both derivatives, and And this term comes from the curvature of the background metric, and also the volume term that basically, well, you can think about it as an analog of tensor network counting the number of tensors, or basically the volume of your optimal geometry. This is also the number of lambda that is related to that so-called cosmological constant, or it's also related to the cutoff as 1 over epsilon square, and it can be actually reabsorbed into the definition, as you can see, by simple shift of phi. So this was at least in two-dimensional CFTs, when we do this optimization, we are minimizing this path integral complexity, which means we have to solve the Liouville equations of motion for this field phi with particular background, with particular boundary condition. And the on-shell value of this Liouville action then gives us the path integral complexity for a given state. There has been very nice works after this proposal by trying to actually maybe give an intuitive interpretation of this Liouville action in terms of tensor networks, for example, MERA. And Bartek was arguing that some terms, like maybe these ones, are that both terms count the number of unitaries and isometries in the tensor network. Also, it was argued that we can do some analytic continuation in the positions of this Liouville field to link it to the kinematic space. And finally, Michał and his group, they made a very nice relation to the works of Gieffre-Vidal and Ash-Milstead, also on geometry of path integrals, and showed that by counting of particular classes of tensors, you can actually approximately also reproduce this Liouville action from that procedure. I'll not have time to talk about this approach, but you can ask also maybe Michał later. So some lessons that we, sorry, does this answer a bit your question from before about the optimization?
Well, my question was more like you have these different meshes. You have a mesh and you're refining it in some way, or coarse graining it.
Yes.
So I was hoping, you could like sort of explain what that is.
I'm not sure if I understand your question. If you're asking if I should explain what different meshes correspond to?
Yeah.
Oh, so yeah, so roughly, this is of course the continuous approach, but you could think about it intuitively as, choosing different metrics on this background as basically some kind of continuous version of choosing different tensor networks. As long as you give each of this plaquette the value of 1, so that you count the tensor net, you have to impose some conditions on the area of these ones. You can think about them as counting tensors in this network in a particular way that depends on the metric G. But of course, this is like inherently continuous approach, so it's hard to make it more precise, at least for the way we understand it now. Okay, so some lessons that maybe that we learned from Liouville, maybe some of them old and some of them new, are that for complexity are that from the Liouville we can see that for universal states, if we take for example vacuum or thermofield double or thermal state or some primaries, we get a generic volume scaling of the path integral complexity, which is something what we would also expect from this holographic complexity. Also, the interesting hint is that by minimization of this complexity or this optimization problem, we get Liouville equation, and this can be shown that oh, sorry, there is some question. So this can be shown that the equations, basically the minimization of complexity in this approach is equivalent to equations of motion of gravity. We can also think about this optimal matrix as some slices of AdS3, where the equations of motion of gravity in 3D imply they are equivalent to the Liouville equation itself. This was also nicely studied by Bartek. In general, actually also Tadashi took it to another level and studied and generalized this procedure to arbitrary, even Lorentzian slices in AdS CFT. And he argued that actually this tensor, we can think about general holographic slices as some tensor networks of path integrals. And he also showed or argued that at least for static cases, the Liouville action seems to be reproducing the value of Wheeler-DeWitt action for complexity. And finally, maybe an older lesson that maybe should put some light on this on the path integral optimization is that, or this path integral complexity, is that actually this Liouville action that I showed you there, if you write it in a covariant way, this is actually the two-dimensional gravity theory of Polyakov, also from a long time ago, and can be written as a central charge and then in terms of the curvatures of the background metric. This 1/box is the green function. I will show it maybe more detail in the next slide. And in this, if you take this covariant formula with this lambda being a cosmological constant and plug this particular ansatz for the metric, this is just a gauge, then you precisely reproduce the Liouville action. And this theory itself has a very close connection with the Schwarzian action. Actually, in the path integral optimization procedure, we can make this also connection in 1D when we do it in 1D. And also give some interesting hints on how this approach might be generalizable to higher dimensions. Namely, we proposed some generalization of the Liouville action in higher dimensions, but also this Polyakov action, at least in even dimension, has a very close connection with so-called Q curvature actions. Okay, maybe one more recap. This is more in the light of summarizing the recent.
Can you say a few words of what that is? A Q curvature action?
Okay. So this I'll not talk more about this, but the Polyakov action itself can be integrated, can be obtained by integrating the anomaly into dimensions. So if you take the Weyl anomaly, so if you take the Weyl anomaly into D, which is basically the proportional to the R, and if you integrate it, you'll get the Polyakov action. In higher dimensions or in even dimensions, we also know what's the anomaly in CFT, and you can try to follow the same method, basically by integrating the anomaly. And this is exactly the definition of this Q curvature actions. If you take your ansatz for the metric in a particular way, or at least for for particular anomalies, let's say A equals to C in 4 dimensions, then you can exactly integrate the anomaly in 4 dimensions, and you're going to get the Q curvature action, which can be also written like relatively like this. This can be written with some Q operator inverse of some differential operator, so-called Panait's operator, and then this Q again. Okay, this will not be important in my talk, but it's just the main message is that the Polyakov action is just a 2-dimensional version of a Q curvature action. Okay, so maybe in the light of recent progress on this or recent developments in complexity, let me also remind you two more things about this Polyakov action. One of it is that well, the Polyakov action is an effective action for gravity in 2D, and actually it's a generating function of the stress tensor correlators. So basically, all you need to know about stress tensor in 2D is encaptured by Polyakov action. And namely, this is the usual generating functional, but we can think about it as taking your conformal field theory, coupling it to the metric, and integrating the matter, integrating over CFT fields. And this is precisely an exponent of minus the Polyakov action for arbitrary metric G. So if you want to think about this pure gravity or pure energy momentum tensor as a toy model for holography, you could interpret Polyakov action as exactly in the light of GKPW formula. This is all you need to know. This is just a partition function as a function of the sources of only the stress tensor. So in particular, the 2 important facts about Polyakov action I will need is that if you take a particular, again, ansatz for the metric, the Polyakov action, of course, is invariant on this diffeomorphism. Sorry, it has the, we don't need to choose a particular metric, but as in gravity action. But if you decide to choose this particular gauge, then actually, as it was noticed by Alexeyev and Shatashvili, this Polyakov action exactly gives so-called geometric action for the Virasoro on the Virasoro coadjoint orbits if this mu is equal to f dot over f prime. And if you take the derivatives of the Polyakov action with respect to mu, this gives you the 1-point function in this gauge. That is the standard 1-point function, say in the diffeomorph in the vacuum state, that in some diffeomorphism of the vacuum that is proportional with the central charge to the Schwarzian derivative of this function f. This is a 1-point function. Maybe also I will need a bit later this, we can expand, for example, in some backgrounds, Polyakov action to the 2nd order to compute 2-point functions. So If you go to your favorite book, at least for string theorists, if you go to Polchinski, you can see that this 1 over box, of course, is just, you can be written as a green function, and the Polyakov action has this form. If we take the green function, say, for example, on flat space and expand this metric to the second order, we reproduce nothing but the integral of the connected 2-point function of the stress tensor multiplied by these two sources. This formula will appear later in some approaches to complexity. So that I just wanted to give some perspective on it at this moment. Okay, this is all I wanted to say about the Liouville action. Are there any questions for now? Oh. Okay, so maybe I should speed up a little bit.
I guess I can ask a question. So yes. Can you say maybe a little bit about what this buys you, the fact that you're relating the Polyakov action to this Virasoro quadrant orbit?
At the moment, nothing, but I'll go a bit late. I'll say a bit late.
Thanks.
Thanks a lot. Okay, how much time do I have? Sorry, I'm not sure if I'm going slow or...
So you have another 10 minutes or so.
Okay, that should be
well,
fine.
maybe technically 7, but
okay, okay, good. I'll try to be fast. So this brings me to the second question, and this was a fun project with Javier Magan that we did during his visit in Kyoto a long time ago. And he was when we were working on this Liouville action, our main motivation was actually not the complexity, but more like how to get the geometry from states in AdS CFT. And Javier was very interested in this Nielsen approach to complexity, and he asked, like, how can we actually marry this Liouville and Nielsen approach, and is it useful to think about this Liouville from the Nielsen perspective? So I'm gonna report to you some findings or some results of this kind of question. And maybe our general motivation was, can you get gravity from Nielsen approach? And in particular, of course, in 2 dimension, that would be Liouville. But in general, how could we think about the Nielsen? How could we aim also in this perspective of AdS CFT, deriving some gravity from complexity? And of course, from what I told you about the AdS CFT, and at least about energy momentum tensor, when you think about gates or circuits, the energy tensor is a natural operator. If something has anything to do with gravity, it has to be energy momentum tensor also by the duality with the graviton. But then this is of course very heuristic and intuitive. But then how do you think about costs? What are the transformations? What are the symmetries? And how to define, how to make this, how to find any overlap between these two approaches. So one hint on that we got from the explicit solution of the Liouville equation. And all the solutions of Liouville equation, this is an integrable equation in 2D, can be written in terms of 2 functions, 2 diffeomorphisms, say f of z and f of z bar. They are in principle independent, and they are just function of this complex coordinate that is tau plus ix. So tau is Euclidean time, x is the position. X can be compact, for example. We'll mostly study cases of a cylinder. And if you think about them at the constant time slices tau, you see that you can think about the Liouville field as a chain of diffeomorphisms for each tau that are being applied by this particular solution. So, so it was clear that if you want to talk about some symmetries or diffeomorphism, you somehow have to disentangle this Liouville field or Liouville action to get closer, to linearize it in some way, or to get closer to these symmetries. And this, of course, is a very old subject. So by the so-called Batlin Transform, we can think this is in fact how Liouville, the Batlin Transform was not known in the times of Liouville, but this is somehow how Liouville solved his equation. And we can write the Liouville action, or there's a canonical map between Liouville action and the free fields. And we can write it in terms of 2 chiral bosons, or as also noticed in many other works among them Alexeyev and Zhatashvili, these are nothing but the geometric actions on the Virasoro orbits. So, so this was one motivation of our work, and that I'll talk a little bit in a second. But the other one, since this is relatively new subject, let's try to see what else is there. How can we maybe define more general costs for these transformations of the energy momentum tensors? Should we make cost state dependent or not? How the cost should scale with C? Should we actually expect some linear growth or not? That was really the motivation behind our work. But let me also tell you a disclaimer that you'll see in many of my references, many of my references are relatively old, some of them even older than me. So some older professor told me that one generation's trash is another generation's treasure. And I just want to stress that the things that we're talking about are relatively old, but very well known, in the sense that we are not introducing any new technology, but we are just trying to reinterpret these old results in terms of maybe complexity or Nielsen approach. Okay, so let me be precise about the setup. We define a CFT, two-dimensional CFT on the cylinder, which has this basic symmetry of two Virazoros, which are just diffeomorphisms of the circle times the R, which is the central extension. And we think about them as just some reparametrizations of the unit circles, these DFS1s. Then in unitary gates are just these representations that I told you, unitary representations of this diffeomorphism that I told you before, and they implement this diffeomorphism on states or on the operators. And then we can define the Virasoro circuit in two-dimensional CFTs as this path, like in Nielsen path and integral exponent of some Q, where this instantaneous gates, you can think about some flow of this diffeomorphism defined by this f of tau and sigma. And for each of tau, in each value of tau, we are implementing some f of sigma. And they are infinitesimally implemented by this energy momentum tensor, as I discussed before, and that we can express in terms of the gate. Now, this symmetric gates, which are the Virasoro generators themselves. The central charge here comes from the fact that we are on the cylinder, so we need to take it into account. And of course, in two-dimensional conformal field theories, we have two copies, and so we just add this Q and Q bar. And maybe in more familiar terms, we can actually write them in terms of stress tensor, or maybe in terms of sum and difference of the stress tensors that are defined as Hamiltonian density and momentum density in CFT. So this is our most general circuit that we can consider into the CFT in the universal sector. In the non-universal case, you might, of course, replace T by some primary operators or descendants or maybe higher currents. But this is, of course, this requires some more work to make it universal. You maybe need to impose some large central charge or maybe some conditions on the spectrum and so on. And then the question of Virasoro circuit would be take some reference state, apply some unitary to get you to the target state. But only using this symmetry gates, and because you're using the symmetry gates, these unitaries are basically path in the group. So this is just the standard definition of the representation. And then Nielsen geometry itself would be, of course, the geometry of the Virasoro group or the Virasoro algebra. This is, of course, the difference between the standard quantum information familiar cases that now it's infinite dimensional, but we know how to deal with that. And we have two copies of this. And we will be looking for geodesics between some initial and non-trivial final point on this manifold. The interesting thing about this is that in this universal sector, in each of these points, or at least with each map f and n bar, we can associate the so-called Bagnados geometry if we give a value of some Schwarzian of this function. So up to some Schwarzian, up to, for some functions that are the same, up to, that have the same Schwarzian derivatives, we can find some Bagnados geometry that correspond to a particular transformation. And also in this case, of course, there is a natural way to think about tolerance because we can distinguish gates, we can distinguish these geometries up to 1/c corrections. So if we really want to distinguish them, we need to maybe we need to specify some other charges like KdV charges or whatever, or some things that is sensitive to 1/c information, but this large C, these two numbers are okay. And now we studied two classes of the metrics. Sorry, maybe I'm running out of time. Yeah, we have two classes of the metrics. We can study state-dependent metrics. This is actually some works that was done before by Javier and also Pablo Bueno and Carlos Chapazzi. And this is basically trying to generalize this formula from the talk of Rob Myers when we have basically when we compute these velocities that we express complexity in from basically taking a trace of some function of the unitary. If we want to generalize this to quantum field theories, it's natural that this trace might be replaced by some expectation value. And of course, this expectation value in these works were defined like two norms, and one norms were defined this way. And yeah, maybe I don't have more time to talk about them, except that they are good norms on the Hilbert space. This is what this guy showed. They are completely fixed by the algebra. So whether you can see that if these guys are expressed in terms of energy momentum tensors, we can just express in terms of the algebra. But at large central charge, they are equivalent. So as you know, in at least for these non-trivial states and on the ceiling there, where one-point functions are non-trivial, then these two norms, the correlations of stress tensor factorize into the products of one-point functions, and they are equivalent. But actually, this two norm looks like a much better thing to study in general, even for a flat space. I will not have time. I'll come back to this question a bit later when I'll discuss the recent results, or very soon. But we can compute these velocities that appeared early in my talk by computing Pawel Transform. This is some straightforward computation, and then the complexity is the functional of these velocities epsilons later. So if we apply these one norms into our proposal, then actually the question is, can you actually see that these one norms, or thing we notice that these one norms are related to this geometric or Alexeyev-Shatashvili actions? And one very kind of naive argument that I'll elaborate in a moment on is that you can already see it on the level of the Polyakov action. So when you take this exponent of the Polyakov action that is defined basically as a generating functional of the stress tensor, you can see that because at large C, the correlation function of stress tensor factorize, so this exponential becomes just the exponential of the one-point function times mu. This is, of course, a rough argument because here we assume, like, this is, of course, true when mu is constant, but in general, this will actually be a little bit subtle, and I'll talk about it later. But if you just follow this procedure, you'll see that by computing one norm, you just need to take this velocity, this mu's here, or this velocity epsilon, and just multiply it by the expectation value of the stress tensor T in the generic state, multiplied by these unitaries from the left and from the right, and that's exactly this guy here. But simply by this argument, at least for classes of mu, this should be equivalent to this Polyakov action. So this is exactly the two copies of Alexeyev-Shatashvili, and hence, or the chiral bosons, and you get the Liouville action. So maybe here also A is related to the expectation value of T in some particular state. This is not important. But already from this action, you can see that if we consider some SL2R transformations, so basically when this Schwarzschild vanishes and this F dot over F prime is equal to constant, as in this case, then you can see that this complexity for this complexity functional gives you a linear growth with this Euclidean time, or sorry, with this time tau, proportional to the expectation value of the energy. This was one kind of rough argument. This was why this was kind of interesting to look. And finally, there are closely related developments due to Virasoro-Berry phases and relative entropy by Hollands and Oblak that I will not have time to talk about, but I can maybe elaborate more in the questioning session. And finally, what else is there? So being more, maybe this Liouville approach was, not maybe trying to marry this Liouville approach and Nielsen approach is maybe not the most most open, most general way to do. And for example, if you want to have maybe more closer to Nielsen approach to this problem of Virasoro circuit, you might try to find, for example, some metrics that don't depend on the costs, that don't depend on the state, as in the case of Liouville. So we also looked at that, at least also in the literature in that, and maybe in Fubini study I'll talk about a bit in a moment. But if we want to have some costs that don't depend on state, then it is a whole very well-known literature on right invariant metrics on the Virasoro algebra. For example, summarized in the books of Kessin and Wendt, that uses the so-called Euler-Arnold method that was nicely reviewed also in the talk by VJ. And we can define a general class of metrics in this way by basically pairing the elements of the Virasoro algebra in this particular way, but also taking care of the central charges of the central extensions. And it is known that the geodesic equation on this manifold is basically equivalent to integrable equations for these velocities and also the equation for the central charges as function of tau. This is the so-called KTV or Kalmasa-Holm or Hunter-Saxon equations that were also discussed, or that were later discussed by Erdmenger and company, and also Michał and Mario. I will say about it in the moment. But of course, the problem of this approach, I mean, there's no problem, but of course, the question is the same. We have very complicated, we might have some simple equation, and that may have solutions. But when we talk about complexity, it's not like we just want to take a solution and evaluate the action, but we really want to find some non-trivial problem, and we have 2 points on this Virasoro manifold, and we want to find the shortest geodesic. So putting the solutions into this form that interpolates between them is a very non-trivial problem. Okay, so I think I'm kind of running out of time. Do I have like 2 minutes to summarize the rest?
Yeah, you can take 2 minutes.
Okay, thanks a lot. So yeah, so there are also very interesting developments on other side of this correspondence between the energy momentum tensors and complexity. Namely, actually we can compute complexity equals volume and complexity equals action for this diffeomorphisms of the circle, or in general diffeomorphisms in the CFT. And this was done by Mario and Nina, and also based on some earlier work by Gautam, Mandal and company. And they actually managed to evaluate volume in a very universal way to the second order by studying some infinitesimal diffeomorphisms, and they got a very nice result. But somehow when you apply it to the CA proposal, Mario showed that that the counter terms that Rob talked about give rise to some particular divergences that look a little bit problematic from the perspective of CFT complexity. Actually, there was a very nice work by Alex Belin, Aitor Levkovich, and Gabor Salosi that were trying to understand better the proposal of information metric by the group of Tadashi. And they generalized the circuits into, they thought about the circuits also in a very nice way by taking some by Euclidean path integral and taking some operators and sources and defining the metric on the sources based on the overlap. So this overlap is basically the partition function of your CFT as a function of sources. Remember the Polyakov action for the AdS for the metric. And then by careful studying of the volume, they noticed that there's a very nice object that reproduces the variations of the volume, or at least, it's very closely tied to the volume that you could propose as complexity. And basically this has this form of more of an energy. These lambdas are basically the velocities, and the metric here is given by the two derivatives are closely related to the Fubini study metric on these sources. I pull back of it, but the nice form of this one is that, again, it's very universal. It can be expressed in terms of some derivatives of partition function, and this metric precisely is the connected two-point function of the operators that you are using. So if you apply it to the stress tensor, they precisely reproduce the variation of Mario. They also did a very nice computation in the lines that you would like to do to get them matching with the linear growth of complexity. They took some mini superspace thermofield double and also recovered the growth proportional to the T, at least in this simple set. And finally, there was a very nice work recently by Johanna Erdemenger and company, trying to remind us that actually we should be a bit more careful what we mean by Virasoro. And of course, Virasoro is the group of diffeomorphism times circles. So the elements are not just this diffeomorphism, but also the central charges. And we should also look at the paths in this group extension. Or in other words, when we talk about the representations of Virasoro, it's not just a product of unitaries has like this, but there's this phase that is very important that tells us that we are not in diffeomorphism group, but in the Virasoro. And they show that when you compute this Mario-Cantan form for that and generalize this one-point function such that it includes this phase, well, this path in the group, then you precisely get the Alexeyev-Shatashvili action as it was recently discussed also in the works of Kotler and Jensen. They also elaborated more on Euler-Arnold and KdV and relation to Berry phases of the nice works by Oblak. And finally, there was a very nice work by Michał and Mario that generalized these approaches of maybe introducing some two metrics in terms of two-point functions in the group. First, actually, they looked at the Fubini study metric for a particular example, and they noticed that you can go beyond the linear order. Fubini study, they noticed that the first order is independent on the metric that you are choosing. So for example, it doesn't depend on if you are evaluating this in the vacuum or in the primary state, but the second order is, and they gave a very nice prediction of what this subliniar order might be. And then they also defined this pi in a more general way in terms of some delta functions, such that the equations of motion become the integrable equations, a la Berger's and Kamasa-Hom and Harmter-Saxton. But if we ignore the phases, of course, they are just not the equations on Virasoro, but on the diffeomorphism. So you will not see the central charge here. But maybe, you know, maybe the message is that it might be enough to compare the diffeomorphisms themselves, and maybe we don't need to go to the Virasoro group in this discussion. This is to be discussed. But also the message from their paper is that we can maybe use more of this complexity geometry to constrain cost functions, and we can go beyond the details of the lengths. We can study curvatures, and this might be the place where some things like geodesic equation might give us some link to chaos and two-dimensional conformal field theories, or yeah, some other developments. Okay, so I'm done. I'm sorry for going over time. I just wanted to say that there's some take-home message that we are still very much in progress. But the one thing that is interesting and clear, that we should think about quantum gates as CFT operators. If we want to be universal, then we should maybe first try to understand energy momentum tensors. Holographic cost functions are still open problem. When we take two Virazoros and one norms, they seem to be closely connected to geometric actions, or more precisely to the Liouville action, as Nielsen, from the Nielsen approach. The Fubini study is very nice and also gives nice results, may be very closely connected to point functions, and maybe good for CV. If we want state independence, then we should focus on Euler-Arnold equations, and it's not, for so far the relation is to AdS CFT is not clear, but it's a vast mathematical literature that may be very useful for us. And we should better understand the complexity geometry and the relation between various computations that I had an opportunity to do after doing the homework. So thanks a lot. This is work in progress, and there's still a lot more to explore. I will leave you with that. Okay, let's all unmute our mics and then thank Pawel. Okay, how am I? So are there any questions?
Maybe I'll ask a question about the Berry phases and the relation to Oblak's work. Can you say some more about that?
Yes. Okay. What did I do to the slide? Okay. So basically this, in this work by Erdmenger and company, yeah, exactly. So then this one norm that they propose here, or this one cost that is basically, so with doing the work with Javier, this psi r is just some reference state that we use as primary. These are the velocities. If you use this Maurer-Canton form, what we did before was just this part, and we ignored the path in the central extension. But actually, if we include this path in the central extension, this is precisely what Blazek calls this is precisely the way that Blazek computes this Berry phase for the Virasoro group. So in a sense that, you know, this one norm, or the complexity with this norm is equal to what he calls the Virasoro Berry phase in his computation. Of course, this is just the technical comment. I don't understand precisely, you know, how the relation between complexity and the Berry phase, at least on some conceptual level, but at least on the technical level, if you use this cost, then the two quantities are equal.
I have a question.
Yeah.
I guess it kind of relates a little bit to the question I asked earlier about what this buys you, and thinking of these geometric actions. So one of the things that's nice about the orbit method is that it gives you a way to take these geometrical things and map them to a Hilbert space through quantization. So in this case, do you have anything to say about what you get by quantizing these particular orbits that you're finding, or how if this gives you, if the quantization of the orbits gives you something useful to say about complexity?
Yeah, I'm not sure. Like, I mean, this is definitely something very important, because we want to exactly understand what is the link between this Nielsen geometry and really the states of your, or, you know, the relation between data of your conformal field theory and these points on the Nielsen geometry. But in some sense, in our case, the role of this Alexeyev-Shatashvili, or basically this chiral boson, was just to make the link between the Liouville. So you might think about it as just, for us, it's important that these are just some kind of West-Zumino interaction or some particle on the group. It's like, if you are familiar with the 3D gravity story, we wanted to somehow go backwards. We wanted to see if Liouville can be seen as some two decoupled particles on the group, and these particles on the group were related to these actions. But we are thinking about this purely in terms of classical, at least in the Nielsen approach, it's kind of a classical statement. It's not, at least the way I understand it now, we don't really want to quantize complexity, I guess, in this Nielsen approach. I'm not sure. But since, yeah, I don't have anything useful to say, maybe some other.
Okay, does anyone else have other questions?
Maybe I can ask.
Yes.
So oh, sorry, Jan, go ahead.
Oh. Yeah, I have one question. So if you, it sounds to me like you're computing the complexity distance between 2 points in some group orbit.
Yes.
And you're not really computing the complexity of a state compared to this mythical, completely unentangled, whatever reference state that volume is supposed to compute. So you're just computing the distance between 2 points in the orbit, right?
Yeah, exactly.
Why would that be related to things like volume and so on? What are you comparing it to?
Yeah. This, okay, good. So, yeah, the short answer is I don't know. The question is maybe why Liouville is related to the volume. So somehow when we compute, when we evaluate Liouville action on shell, we see that it is related to the volume of this background metric, because somehow this metric happens to be the same as the time slice of AdS. So when we think that, personally I tend to think about this, the geometric actions as simply two copies that just give me Liouville. So if I combine them appropriately, I should be able to get from them the same volume as I'm getting from the Liouville. And your question is exactly about like why are we getting this volume from Liouville? And I don't know exactly.
I just have a remark to Jan's question. So one thing that you can do is you can evaluate the volume for the ground state and the volume for, say, a diffeomorphism of AdS3, and subtract these two, and you're going to get a UV finite answer. And then you can ask a question if subsequent terms in the expansion on top of, in the magnitude of the local conformal transformation are going to match the result of any of these calculations. And it turns out, as was shown by Gabor, Alex, and Aitor, based on the work by Mario and Nina, that the leading order actually matches if you use Fubini study. But you can also try to compute the higher order ones and see if they match in any way. This has not been done yet. The comparison has not been done yet.
It will be a bit, so you're having 2 points that are related by Virasoro, and you're computing these two distances to this unknown reference state. And in principle, it's a triangle of some sort, right?
Yeah, it's hard to believe that you would get an exact agreement. But you can well, and like that's probably the best you can do using holographic complexity for now. So I suspect that's a good idea actually to do such a calculation to see what comes out. But from the point of view, like just to close this thought, like from the point of view of Fubini study, you can change the state in which you evaluate it. You can call it even reference state to be something else. And like if you come back to the CMERA construction, CMERA, you use effectively a spatially disentangled state, and this actually has a strong resemblance to the story of surface state correspondence by the Kyoto group. So I mean, I think there is a room to maneuver within this whole idea that we still haven't explored as a community. But maybe it's a good topic to discuss after both talks, actually.
Yeah, so I think we're running a little bit late on time, so we should Maybe if there are further questions, we can continue in the discussion after the second talk. So for now, let's just thank Pawel again. Everyone can unmute and thank. And now we'll take a 5-minute break, and then we'll start at 10:16 this